Yes, sir. The control is given, sir.
Yeah. Good morning, students. Am I audible? Hello.
Yes, sir, you are audible.
Thank you. Okay, so today we'll start our discussion on a new subject, which is fluid mechanics. So coming to the gate point of view, these cars around 6 to 8 marks. 6 to 8 marks. Very, very important. It's like if you see in a mechanical syllabus sheet, the first preference will be given to the production, in terms of weightage. The second will be given to mathematics. Then comes to thermodynamics, followed by fluid mechanics. So this is how the subjects are weighted based on their marks. So what I suggest here is, based on the weightage, you try to spend time also. Like, more the weighted subject means you try to spend more time on that subject, so that you should score more number of marks. That's what the equation. So now coming to fluid mechanics, these are around 6 to 8 marks. These are around 6 to 8 marks in the gate point of view. Let me give you the syllabus first. If you see the syllabus, we'll start with the first chapter, which is called as basic concepts. Assuming that we don't know anything about fluid mechanics, we'll introduce some technical terms which generally people talk when they're discussing about fluid mechanics. So those kind of technical terms we'll introduce in the first chapter, which is called as basic concepts. It's like the fundamentals of this subject. Coming to the next one, assuming that we understood something related to technical terms of the fluid mechanics, we'll jump into the next chapter, which is fluid statics. So the name itself indicates here, it's a statics, so which means the fluid, when it is at rest, we are going to analyze the problem. So what are the kind of forces we'll be seeing? So those kind of things we'll see in a chapter called fluid statics. This is very similar to what you learned in your engineering mechanics, nothing different. Only thing is, instead of talking about a rigid body or a solid body, we are going to focus on fluids, maybe liquids or gases. So after understanding the problem, when a fluid is at rest, we'll jump into some real problems. Which is when fluid is in motion. That is what is called as fluid kinematics. Again, this is very similar to your engineering mechanics. There also we are learned, you may be learning kinematics, a similar kind of chapter here also, which is kinematics. That means we mostly focus on like basic parameters when a body is in motion, something called displacement, distance traveled, velocity, acceleration. So these kind of terms. Apart from that, we'll introduce some more new terms related to fluids. That is what is called as fluid kinematics. Followed by knowing some basic terms when a fluid is in motion, how to describe the fluid. We'll jump into the forces. That is what is called as fluid dynamics. Very, very important. Fluid dynamics. So in this chapter, we completely focus our things on when a fluid is in motion, what are the different kinds of forces that need to take care. Similar to statics, but a little complicated, because apart from rest, you're adding some more extra complexity to a fluid when it is in motion. So that's why some extra terms has to be taken care in a chapter called fluid dynamics. So these dynamics, again, to make our things simpler, we'll divide into 2 chapters. That's very important. We divide into 2 chapters. we'll divide into 2 chapters. What is that means? Fluid dynamics when it is a inviscid flow. Inviscid flow. Fluid dynamics in the case of viscous flow. Viscous flow. So very, very important. In the exam also, you need to identify whether the question is given in inviscid flow or a viscous flow. That is very careful with this. Inviscid flow, viscous flow. So we'll come to those kind of things in detail when you go to the particular chapter called inviscid flow and viscous flow. But broadly speaking, in the first part of fluid dynamics called inviscid flow, we generally neglect the important force component called as shear force or viscous force. That is what is called as inviscid flow. Whereas you try to include that extra complexity of shear force also, that is what is viscous flow in the case of fluid dynamics. In the case of fluid dynamics. Fine. So then we'll go to the next one, which is pipe flow, So that means after learning all these basic understanding of your fluid mechanics, we are going to focus on a completely real problem, especially for both civil and mechanical, like where you want to transport some fluid from one place to another place using some kind of pipes. So how to design these pipes so that it can withstand the forces exerted by the fluids. This is a common problem in reality. In any industry or any place you go to work, you'll be seeing these kind of problems in very common. So that's why you need to know in hand what are the basic things you need to think about in designing a pipe when it is exerted by some kind of forces by the fluids. Different kinds of fluids. That's very important here. That is what is dealt by a chapter called pipe flow. So then comes out the last chapter, which is compressible flows. This is not for civil. Please make sure this is not for civil people. This is only for mechanical and aerospace people. But here anyhow, aerospace people are not there. It is particularly meant for mechanical people. That too they have included in the syllabus. I think last year. This extra portion they have added. Whereas up to 5 chapters, it is same for both civil and mechanical. Only for mechanical, the extra portion they have added, which is called as compressible flow. So what does that mean? Up to 5 chapters, a very important assumption here is up to 5 chapters, a very important assumption here is incompressible flow. We'll see all those things a little later, but I'm just giving the things a little bit now so that you will be getting some kind of grip on the syllabus. Up to 5 chapters or up to 5th chapter, a very important assumption in our entire study will be incompressible flow. Whereas in the 6th chapter, if you neglect the assumption called incompressible flow, what are the extra things that you will be taking care? That is what is called as compressible flow. So broadly speaking, what is the purpose of studying from 1st chapter, 6th chapter? Means you are slowly increasing the complexity of the problems in nature. We're slowly increasing. Like in a statics, the complexity is very minimal. Like you are going to talk about only the basic forces, like 1 or 2 forces. Whereas slowly when you're increasing the complexity, or when you're going from one chapter to another chapter, you're slowly increasing the complexity of the problem. That means you're adding more and more forces to the problem. So problem is getting complicated, and you should know as an engineer how to handle these forces so that you can design any component through which you want to send some fluid, or you want to transport some fluid. These kind of things are very common. Like when you go to reality, a basic thing, suppose if you want to ride a bicycle, so you need to design the bicycle in hand so that when a person is riding a bicycle, it should withstand the forces exerted by the surrounding air when it is in motion. So that's why this fluid mechanics is very, very important in each and every part of our life. Like if you see nowadays, people are exploring this fluid mechanics by linking into our body parts, body organs, something like how heart functions. Like there also you'll be having blood instead of water, air and all, you'll be having a different kind of fluid called blood. So where the blood flows through arteries, veins and heart. So you'll be having some kind of pipes, but they are not like a rigid pipe what you see in reality like our mechanical applications. In these kind of biomedical applications, they are having flexible pipes, is right. The arteries, veins and all, they're very, very flexible, not like you're rigid. So into which you're transporting a fluid like a blood, which is different from your water and air. So you should know in hand this fluid dynamics of that blood flow, so that you can arrest or you can rectify blood clots, or you can postpone the heart attacks. These kind of things people are exploring nowadays. On the top of that, people are exploring the things like stomach related things. Like there also you'll be having an intestine, you'll be having some blood flow there also. So people want to understand how a fluid mechanics or fluid dynamics will be in those kind of problems. That is related to biomedical. So on the top of that, if you come to our mechanical applications, like if you see all the moving vehicles, all the moving parts in our reality, like aircraft, when it is flying, it has to be designed very clearly based on our fluid mechanics knowledge. Otherwise, the aircraft may fail during its run. So as an engineer, you should be very good at applying these kind of concepts, whatever we are going to learn in the class, in order to design each and every component of an aircraft. That is completely related to our fluid mechanics. Without these, aircraft cannot be designed. Number two, whatever cars, buses, all are rockets, all these things, they're completely governed by a important subject called fluid mechanics. On the top of fluid mechanics, you'll be having thermodynamics, you'll be having heat transfer, you'll be having strength of materials. Why? Because in all these kind of problems, a common thing is there is a fluid flow. It may be air, it may be blood, it may be water, whatever may be. But there is a fluid mechanics involved in that, especially fluid dynamics involved in that, because of the motion. So that's why it's very important when you're working with these kind of problems, you should know some fundamentals about fluid mechanics. Coming to statics, let me give you some examples about statics. Like a basic thing is in our overhead tank, like in our house, we have an overhead tank. So where we store some water, whenever there is a demand in our household application, we open walls, we open tap, we get the water. But for a period of time, the water is under rest in that overhead tank. So this overhead tank has to be designed properly to withstand the forces exerted by the fluid on the tank over a period of time when the fluid is at rest. So therefore, this job is done by the engineer. Any overhead tank, the forces has to be considered based on fluid statics chapter. I'm giving a very small example. The real life example will be something like related to your power plants, where you store some water for sending it to a boiler for heating water to convert into steam. Similarly, in big industrial applications, people usually store a lot of liquids or a lot of molten metals. If you see production and all, casting, welding, manufacturing process, you'll be having a lot of molten metals. So there also they will be storing a lot of these kind of liquid form of material in big tanks. So now, as an engineer in hand, you should have done the design of the tank properly to withstand these forces exerted by the fluid, because the fluid is at rest inside the tank. So it will exert some forces on the tank. We'll come to know what are the forces on the little later, but I'm just giving the feel for the subject. Where are the places where you will see this subject in reality? Similarly, suppose if you want to transport suppose a milk from one place to another place, suppose milk is not available in a given place, milk is means the availability of milk is very good in a particular place. Suppose you need to transport from that place to another place, we use some big tanks to transport of milk or petrol or whatever, any fuel. So the tank which is carrying these fluids has to be designed properly whenever a fluid is at rest during the transport. Otherwise, a lot of wastage will happen. So therefore, an engineer who knows these fluid mechanics concepts is very, very important in these kind of real examples. This is very, very important. Is very, very important. Again, one more simple example is in all of our houses we use LPG cylinders. So there also the gas which we are going to use for a burning for our cooking purpose will be stored inside the cylinder at some pressure and temperature. So that is also under rest. Under rest. If you are not using, that will be under rest. So therefore, in hand, engineer has to design that cylinder. What is the thickness? What kind of forces are there? How much is the value of the force? So to withstand the forces, what kind of material you have to choose? So these kind of things, or these kind of calculation has to be done in hand, so that there won't be any problem in future who are using the cylinder. So that's why this fluid mechanics is very, very important. So any questions on this syllabus and the applications? I'm just giving a feel for the subject so that you guys will appreciate the things. Why you are learning fluid mechanics is very, very important. It's not like simply you are going to sit in some class, you are going to learn some subject. It's not like that. So always ask a question as an engineer, why you need a particular subject in learning? What's the need in reality? Do we need really this kind of subject, especially for your engineering applications? Do you need or not? You please ask a question on yourself so that you'll get some feel for the subject. Then automatically the interest comes while learning. That's what I do always. Like whenever I'm reading any subject, I take care of all these kind of things. It's very important. So these are syllabus. This is syllabus, very important. Please make sure always a syllabus a must. Like you should know or you should see what is the boundary of a given subject. It's not like a boundaryless thing. You should have some boundary for subject, because you are preparing for a competitive exam. You should know what is the syllabus they are choosing to prepare a question paper, so that you will be comfortable in answering the things when you prepare well. So that's why I always give a syllabus like kind of chapters, like based on the syllabus sheet what they have provided. So this is syllabus based on a previous year. I think no more additions will be there. I think this year always, they have added enough syllabus up to now. So the extra thing is the compressible flows for a mechanical people. So we'll see the syllabus a little later, because in this class both civil and mechanical are sitting. So therefore let us focus on the first 5 chapters first. We'll see these compressible flows a little later. That's not a big deal. And coming to the textbooks, textbooks are very, very important. Please, apart from reading notes, you just follow some good textbook. That's very important. Try to follow a textbook like Fluid Mechanics by Chandru, or Fluid Mechanics by Fox, or Fluid Mechanics by F.M. White. Don't follow any local author and all, because these textbooks generally people prefer, like the people who are setting the question papers. That's what I observed from the previous experience. Like the previous questions, they just copied from these textbooks just by changing the numbers. So always try to read these textbooks and try to solve the unsolved questions in these textbooks in hand, so that it will be easy for you guys when you go to the exam. And you can follow textbook by S.K. Som and Suman Chakravarti. From IIT KGP. So these textbooks are very good textbooks. I think these are more than enough for your GATE preparation as well as IES preparation. Not a big deal. But follow these textbooks only. Don't go with some local authors and all. Because a lot of mistakes will be there. But these are standard textbooks. Fine. And if you have any queries, you can we can discuss in the class itself. Or if you want, you can watch NPTEL videos from the same IIT Kharagpur by the same professors. They have a textbook as well as the NPTEL videos. You can see in YouTube also. You can watch these videos, no problem. So any questions up to now? Anywhere, any doubt? So these are the textbooks. This is syllabus. Fine. If it is clear, let us. So this what is the applications point of view. You need to see the subject first, then the syllabus, then the textbooks. This how you need to see any subject whenever you're learning any subject in mechanical or civil, whatever the stream may be. Think about the subject something like what is the use of this subject as an engineer, as a particular like mechanical engineer in my reality. You should ask a question on that, and based on that, see the syllabus, whether the syllabus is going to relate to your application or going to solve your problem or not. If I learn this kind of thing, whether it will help me in solving a particular problem in reality or not, you should check these kind of things. Then to understand the syllabus or to understand to read the syllabus, what are the kind of textbooks or what are the kind of materials I need to follow. So that's it. So now coming to the first chapter, like basic concepts. Let us jump into the first chapter, which is basic concepts. So any doubt on syllabus, textbooks, anywhere, any questions up to now? Do you guys are fine? Fine. Okay. If it is clear, let us see first what is meant by fluid mechanics. Let us define, or let us see what you're going to read first under fluid mechanics. Then we'll go for introducing the new technical terms under fluid mechanics. So please assume that I know most of the people are in final years or third years, but please assume that you don't know anything about fluid mechanics. Let us start from zero. Let us start from zero and leave whatever you have learned in your BE or B.Tech level in your classrooms. Leave about that. Assume that you don't know anything and try to learn from scratch. So coming here, I'll divide this fluid mechanics word into two words. Like first one is mechanics. First one is mechanics. The second one is fluid. First one is mechanics. I'll take this word out. First one is mechanics. Then you will see fluid. Anybody, what is meant by mechanics? What is meant by mechanics? I think you might have seen the same kind of word like mechanics in the remaining subjects also, like engineering mechanics, solid mechanics, right? There is another one like continuum mechanics also, which you will be seeing like when you go for higher education. So in all these things, a common word is mechanics. A common word is mechanics. Let us define what is mechanics. So please be careful with this term called mechanics, very important. So wherever you see a term called mechanics, means you are going to study bodies which are under rest or in motion. First of all, number one, any body, and whether it is a fluid, a solid, fluid means liquid, gas, doesn't matter, but the body has to be studied both when it is at rest or is in motion. Number one. And number two is you are interested in types of forces exerted on that body when it is in rest or when it is in motion. So that kind of study is done under a subject called mechanics. So very important. Let me define that term, mechanics. Let me define the term called mechanics, which is like a branch of science which deals with bodies under rest or in motion. Very important. These two terms are very important. Rest or in motion. A branch of science or branch of physics which deals with bodies under rest or in motion. But a primary concentration will be, our primary focus will be calculating the different kinds of forces. Very important. This is a very important thing in any mechanics. any mechanics you see, like whether you play with engineering mechanics or a solid mechanics or a fluid mechanics, our primary focus will be on forces. What are the kinds of forces in that particular problem? How you deal those forces, like what is the direction, what is the magnitude, because force is a vector. We know that from our school level physics. Force is a vector. A force is a vector. So you need two things. One is a magnitude, similar to scalar, whereas you need one more thing here, which is a direction. What is the direction of the force? So please be careful with this statement. We'll be using this kind of analysis in our entire fluid mechanics. Any chapter we go, whether you start with statics or you go with dynamics, inviscid, viscous, compressible flows, pipe flow, whatever may be, our primary focus will be on force. On the top of that, we'll be dealing with two things parallelly. One is what is the direction of that force and which direction you are going to focus. Number two is the magnitude of that force. What is the value of that force? And we'll be seeing varieties of forces depending on the types of problems we are going to have, like different chapters particularly. We'll be adding one on the top of the other. Like if you see statics, we'll be having some basic forces like one or two. Then when you go to dynamics, inviscid flow, we'll be adding one more. We'll see what is that one more, what's the name of that one more, we'll see later. When you go to a very important problem like viscous or pipe flow, we are going to see an extra one on the top of the existing one. So it's like addition and subtraction of forces, with direction and magnitude. So that's the main importance of a subject called mechanics, main important concept called mechanics. So now in these particular mechanics, we are going to focus on very important thing called fluids. Very important. We are going to focus on fluids. Please be careful with this word. So it's not like your engineering mechanics, because in engineering mechanics, it's completely a solid body. In engineering mechanics, it's completely a solid body. Let me write here. Please see this difference, very important. In engineering mechanics or solid mechanics, or solid mechanics, you might have used or studied the things based on solid bodies. It's very important. Solid bodies. Whereas in this particular subject called fluid mechanics, will be focused on completely fluids. So fluids means these are like two things that we know already from our school level physics. One is liquids. The other one is, the other one is gases. Fluids means number one liquids, number two gases. So that's why a new subject came into picture. Otherwise, you might have closed everything in that subject itself, like engineering mechanics or solid mechanics itself. We might have closed the mechanics related to your mechanical engineering or civil engineering. But there is something extra that you need to learn for fluids. That's why you are describing all those things under a different subject, or studying all those things in a different subject, which is called as fluid mechanics. So mechanics is same. Whatever you are done, the type of analysis you are done in a previous subjects like engineering mechanics or solid mechanics, the kind of procedure, the kind of things, all are similar. Only thing is, we'll be completely focused on fluids, especially liquids and gases. So in the exam also, you need to differentiate the question. Because in both the questions, things will be talking about like forces only. In whether you take a problem like solid mechanics or you take a problem from fluid mechanics, a problem will be dealing mostly on your forces. So therefore, whether they are talking about a fluid or a solid body, you need to differentiate that first. If the problem is talking about a solid body or a rigid body, that means they are talking about an engineering mechanics or a solid mechanics problem. If they're talking about a particular fluid like liquid or gas, any water, air, mercury, blood, any kind of fluid, any kind of fluid or any gas like nitrogen, oxygen, carbon dioxide, these kind of thing. That means they're talking about a fluid mechanics. The kind of means if they're interested in forces. If they're interested in forces, please be careful. I'm talking about forces. The same liquids and gases you might have used in solids, you might have used in thermodynamics, heat transfer, any other subject also. But there you don't focus about forces. There the interest will be something else. There the interest will be something else. But the subject which is focused on forces is fluid mechanics. Fluid mechanics. Now the next question here is, already the things are similar. Other things are similar, like compared to solid mechanics and fluid mechanics. Why you want a separate subject? Why you want a separate subject? That's a very important question. That means, what is the difference between fluids and solids? That's very important to ask. That's where the subject lies on. What is the difference? What is the difference between fluids and solids? What is the difference between fluids and solids? Anybody? Any idea on this?
Fluid is a kind of thing that deforms continuously under action of any load.
Very good. What about solid?
In case of solid, it will give an instantaneous displacement, not continuous.
Okay, very good. Yeah, exactly. So let me define in little different, but whatever he said is completely okay. So thing is, in solids, if you apply some force, any kind of force, it start to deform. It will start to deform once the load, the force, whatever you're applying, if it is exceeding its resisting capacity. So any solid body will have some resisting capacity that we know. If you're giving a load which is more than its resisting capacity, it will start to deform. It will start to deform, and the deformation you are going to see will be a finite value. And the deformation you are going to see will be a finite value. Like if I take a solid board, box or block, whatever maybe, something like this. Something like this. Okay. I have two kinds of forces that you might have learned from your basics of engineering mechanics or solid mechanics. So let me give you that also, just for understanding purpose. Forces. This is not from fluid mechanics. This is a universal statement. Like I can say, like universal statement. Forces means a kind of two types. One is a normal force. The other one is a shear or a tangential force. Please be careful with this. Very important. Any force in nature, we are going to separate it out like two combinations. One falls under a normal force, the other one falls under a shear or tangential force. So normal force means if a force is acted perpendicular to a given cross-sectional area, then the kind of load or a force is called as normal load or normal force. If a force is applied parallel to the cross-sectional area, if a force is applied parallel to the cross, that means it is trying to slide. The force is trying to slide the body, or shear the body. That means one layer of the body is moving relative to the other. Then that kind of load is called as shear or tangential force. Okay, so these are broad statement for any kind of mechanics, whether you talk about solid mechanics, engineering mechanics, or fluid mechanics. These are broad statement for forces. Like any force has to fall and means in between these two categories. Like it has to be a normal force or a shear force. So that is very important. Like let me give a pic here. If it is a normal force, if I have a body something like this, suppose say, my load will be something like this. This is what is normal force. If I'm applying the same load parallel to the cross-section area, that means this layer moves relative to this layer, then this kind of load is called as shear or tangential load. Very important. That means here you're applying perpendicular to the cross-section area. These are cross-section area. Please be careful with that. These are cross-section area. Actually, the picture will be a three-dimensional picture, will be something like this. So you are applying perpendicular to the cross-section area, whereas in this case, in the second case, you are applying parallel to the cross-section area. The same cross-section area, but the load is parallel. In the first case, the load was perpendicular. Now the load is parallel. parallel. So these are the two kinds of forces which you will be seeing in any kind of mechanics, any kind of mechanics. Now let us come to fluids and solids differentiation with understanding these kind of forces. Let me take a shear force. Let me take a shear force. Let us assume that I'm having a solid body here. Suppose say the first case I'm choosing a solid body because this is what you have learned already from your previous subjects. That's why I'm first choosing a solid body. I'll apply some shear load, some Fs, suppose say. Let us assume that this bottom is fixed for our interest. This bottom is fixed. And let us assume the Fs, whatever you have applied, is greater than the resisting force, suppose say. A little greater than, not like a huge value, so that the body may break. We are not going to deal those kind of things. A little higher than a resisting force of the solid body. A resisting force of the solid body. So if this is a situation, I mean, the result will be something like this. A result will be something like this. That means after some time, you will see the same solid block might have sheared like this. Or let me draw here itself. So this is what is after applying load. After applying load. After applying load. After applying load. And because of this, you are going to see a deformation. You are going to see a deformation. In these kind of shear loads, we measure the deformation as shear strain. As shear strain. This is what is some theta. This angle represents shear strain. This is what you might have learned in your engineering mechanics or solid mechanics, shear strain. And this is what is shear load that we have learned just now, parallel to the surface, parallel to the cross-section area. This is what is shear load. Parallel to the shear load, I mean surface, which is called a shear load. So now the thing is, if you wait for suppose some period of time, say this what has happened at suppose some after applying load, after some 5 minutes, if you wait for some another 10-20 minutes or 1 hour or 2 hours, doesn't matter, the value of shear strain will remain same. The value of shear strain will remain same until and unless if you change the load. If you fix the load, suppose say Fs is suppose say some 10 Newton, suppose say a 10 Newton, suppose say if you applied some 10 Newton, if you fix the 10 Newton, if you're not disturbing the 10 Newton, the value of a theta or shear strain will remain same for any time you take. For any time you take. That is what is the scenario in the case of a solid body. That is what is the scenario in the case of a solid body. Let us jump into fluid. Suppose let us see what will happen in the case of fluid. Is it clear, everybody? This is what you might have learned in your engineering mechanics and solid mechanics. I'm not dealing any new thing here. I'm just focused on a shear load. I'm seeing what is happening to that. And let us go to a fluid mechanics problem, or especially fluids related problem. Suppose say suppose I have 2 plates, a top plate and the bottom plate. These are 2 solid plates. These are 2 solid plates. Let us assume that the fluid is filled in between these two. Fluid is filled in between these two plates. Let us assume that somehow you have managed to keep the fluid at rest initially. At t equal to 0, let us assume that the fluid is at rest. At t equal to 0 implies a fluid between the 2 plates is at rest. Very important statement. Fluid is at rest. Now what I'll do for little higher time. So let us assume that for a t greater than 0, a little greater than 0, what I'll do, I'll apply some shear load on the top plate. shear load is applied on the top plate. Again, the same situation. Shear load means a load applied parallel to the surface. A load applied parallel to the surface is called a shear load. So I'm applying a shear load here. Shear load here. Whatever with the load doesn't matter. Even if it is very close to zero, also doesn't matter. Whatever with the minimum doesn't matter. There is no constraint to the load now. In the previous case, there was a constraint. We kept a load a little higher than the resisting load. Then we saw some kind of deformation there. Whereas now there is no constraint on the load. Any minimal load doesn't matter, but should be a little higher than zero. Little higher than zero. So in that case, what I'll do here, what I'll see here, this what is a t equal to 0, which is at rest. Now, if I go for a later time, say t1, t2, t3, whatever may be, which is greater than 0, a fluid, here also the shearing will happen, similar to your solid body. But there is a little difference between the previous solid and the present fluid. Little difference between the previous solid and the present fluid. So what is that means? It starts to deform continuously. Irrespective of what kind of load that you have applied there, what is the amount of load that you have applied there, doesn't matter. Whatever with the minimum doesn't matter. It just slowly deforms, continuously deforms. I'll give you the time. Suppose say the first dotted line is suppose a T1. This is a T2. This is T3 of suppose a left end. Similarly for a right end, at the same time T1, a T2, T3. And you see this a T1. This is a T1 is less than T2, is less than T3. So that means you wait more and more time, you'll be seeing continuously more and more deformation. Again, the deformation, how you measure means it's a similar story, nothing different here. It's similar story. What is that means? I'll draw a vertical here. Let me take orange. So there is a vertical sitting here. Sorry. So I'll take that thing out. So having a vertical shade. What is that? You're having vertical here. So you have a θ1 at T1. You have θ2 at T2. You have a θ3 at T3. It's very important. This refers to T1. This refers to T2. This refers to T3. Are you guys clear? Whereas a θ1 is not equal to θ2, is not equal to θ3, but this is a function of time. It's very, very important conclusion. This is what is making our solid mechanics completely different from fluid mechanics. In a solid mechanics, you have a fixed value of deformation or strain, whereas in a fluid mechanics, you don't have a fixed value. Even though you kept the same load, a fixed load for a period of time like from T1 to T3, but the value of strain or deformation you are going to calculate with respect to time, they won't be same. It will be continuously deforming. So therefore, it's very important to study the subject separately. That's why we are dealing the subject separately, which is called as fluid mechanics. On the top of that, we are not going to call here as a strain. The term is defined here as with a different kind of term, which is called as a rate of strain. Rate of strain. Please be careful. This is very, very, very important term, which is making your fluid mechanics different from solid mechanics. Rate of strain. So we are interested in rate of strain now, not the value of a strain at a which was a fixed value in the case of a solid mechanics, which is not a fixed value in this case of fluid mechanics. It varies with time. You should know what is that function, what is theta function of time. So then you can calculate at a given time, this is what is the value of shear strain. This is the value of shear strain. Any doubt, anybody? Any questions anywhere? Understood the difference between fluid and solid. So here there is no constraint on load. Any load is fine. It continuously deforms. Any load is fine. It continuously deforms. Whereas in solid, there is a constraint on the load. You should have some particular load. After that, only you see some deformation. That is from our common sense. Like you see any load in your home or whatever, maybe any object, you apply some load, it will not break or it will not deform. It has some particular load after which it starts to deform. That is what is a solid body kind of story. Whereas in coming to fluid mechanics, it doesn't matter. Any small load doesn't matter. It starts to deform, continuously deforms. So that's why you should talk here not as strain as like what you see in solid mechanics. You should specify with a term called a rate of strain. A rate of strain, very important. Rate of strain. Is it clear? Any questions? Anywhere, any doubt? Arasu, Arun Kumar, Ashwin, Balaji, Dinesh, Deepak, and let me see the names. Galaxy, it's not a name. I think it's a mobile name, right? James, Sneha, Surender, Ashwant. Any questions? Fine. Okay, good. Thank you. So if it is clear, so this what is the basic difference between your fluids and solids. Let us jump into the technical terms. Let us jump. Already we have given one technical term, which is rate of strain. That is very important, but we are not going to use this rate of strain kind of term now itself. We'll be seeing the importance of this term once you develop the actual concepts. We'll keep this aside just to define a fluid and solid. This is what is helping us. Let us see some more technical terms related to fluid mechanics or fluids, especially which you didn't see much in your solid mechanics. Let us see those kind of terms now. The first term, basically we call those kind of terms as properties of fluids. We call those kind of terms as properties of fluids. Properties of fluids. So this is what is called as basic concepts. Under that, we are calling first topic as properties of fluid. We list some properties of fluids, which are very important to describe a fluid. Like it's like describing a person. If you see some kind of say a celebrity or a cricketer, whatever maybe, you describe him with some properties. Like if you see Virat Kohli, you see like his strike rate is something. Based on that, you describe that person. Like the same way, fluids also has to describe with some kind of terms. Let us introduce those terms first, then we'll jump into the actual concepts of fluid mechanics. In that, the first one, the property that we are interested here is a density or a mass density. Density or mass density. Density or mass density. Generally, we use a symbol called rho or HO. Rho. Density or mass density, rho. I think this is very straightforward definition, nothing complicated here. Defined as mass per unit volume. Defined as mass per unit volume. So if I take 1 meter cube of volume, what is the mass of a particular thing? This is actually, this kind of term is helpful in describing solids also. but we use that term more rigorously in a subject like fluid mechanics. That's why I want to introduce term here again. It's like mass means mass of your molecules. You have some n number of molecules inside 1 meter cube of a given volume. In that 1 meter cube, you count the number of molecules. You count the number of molecules of a given fluid or a solid, whatever may be, fluid or a solid, whatever may be, and you count the number of molecules, multiply with mass of each molecule. Mass of each molecule, you'll get the total mass of the molecules divided by the volume will give us a density or a mass density. So it's from our common sense, it's very clear. In a solids in 1 meter cube volume, you'll have more number of molecules, which leads to more mass in the same 1 meter cube compared to liquids, compared to gases. The gases, you'll see a least number of molecules in 1 meter cube volume, so which leads to lower density, Very, very important. So now if I write in a mathematical expression, density rho is equal to mass per volume. Mass per unit volume. So what do you expect the units of rho? Units for rho. Mass units is a kg. Volume units is a meter cube. So therefore kg per unit. Kg per meter cube. This is what is SI units. If you want, you can convert into CGS also, which is equal to 1 kg is 1000 grams divided by 1 meter is 100 centimeter. So 10 power 6 centimeter cube. This conversion is very important. Please be careful. 10 power minus 3 gram per centimeter cube. 10 power minus 3 gram per centimeter cube. So please try to understand the definition, meaning of the definition. It's not like you need to learn or mug up the equation. I don't prefer those kind of things. So what's the meaning of this is, if I take 1 meter cube of volume, like if I have a volume of 1 meter cube, for any substance, whether it is a solid, a liquid or gas, it doesn't matter. This is a 1 meter, 1 meter and 1 meter. I have a lot of molecules sitting here, some n number of molecules sitting here. So what I'll do, I'll calculate the mass of these molecules, then divided by 1 meter cube volume. That is what is representing density. It's very similar to a population density, what you see. Like if you take 1 meter cube of space, 1 meter cube of space in a given city, suppose say, you count the number of people living in that 1 meter cube, it represents a population density of that particular city. Population density of that particular, like a good example is Delhi will be having a more population density compared to Bangalore, compared to Chennai, compared to Hyderabad. That is obvious, right? You know that from our common sense, more people will be living in a given 1 meter cube. It's not 1 meter cube there, it will be a different unit, but in a similar kind of story, I'm just taking 1 meter cube. How many people are living in that? Instead of people, we're having molecules here. A similar kind of thing. Here, there you count the number, but here you need a mass of that. So therefore, you need a molecular mass multiplied by the number will give us the total mass, divided by the volume will give us a density of that given substance. So always you expect more number of molecules will be sitting in the case of a solid in the same 1 meter cube compared to liquid than gases. Gases will be the least. So the expectation will be something like this, which leads to density of the solid is greater than, actually speaking, much greater than, okay, density of the liquid greater than density of the gas. This we might have learned in your school level physics. I'm just giving again the same kind of things. Okay, that is from our common sense using this statement, nothing different. A good example will be a density of water. Density of water is 1000 kg per meter cube. 1000 kg per meter cube or 1 gram per centimeter cube. Please be careful. 1000, it's 10 power minus 3 here. So therefore 1 gram per centimeter cube. If I go for air, see the difference, very important. Please feel the numbers. If I take air, I'm having almost 1 by 1000, that is 1 kg per meter. If you take air, the value will be around 1,000th of a water, 1 kg per meter cube, or 10 power minus 3 gram per centimeter cube. Please feel the numbers. It is very important when you go to interviews. In interviews, they'll ask you, what do you expect the density of air? You should not say something like 500, 1,000, 2,000 and all. It's completely wrong. So please be careful. The air, gases and all density will be close to 1. Close to 1. Whereas liquids, they'll be having 500, 600, 800, 1,000. Any liquid, most of the liquids, whatever you use, like oil, petrol, kerosene, all these things, they'll be close to 3-digit numbers, 500 to 1,000. Whereas if you take solids, they'll be having around 2,000, 3,000, 8,000, those kind of numbers. That is expected again. And one more thing you need to keep in mind here: this density is a function of pressure and temperature. This density is a function of pressure and temperature. That is expected. That is from our common sense. Like if you change temperature, you will see this number of molecules sitting inside this 1 meter cube will change. Similarly, if you pressurize or depressurize, you will see again the number of molecules will change here. So which leads to change in density. It's very, very important. Density is a function of pressure and temperature. Pressure and temperature. But very important conclusion here is for liquids, a density won't change much with pressure, but changes with temperature. That will prove a little later also, but I'm giving one more statement here. Please be careful with this. Density is generally a function of pressure and temperature, but in the case of liquids, density is not a strong function of pressure, but it's a strong function of temperature. It's a strong function of temperature, but it's a weak function of pressure. It's a weak function of pressure. Whereas for the gases, it's very important. Whereas for the gases, it's a strong function of pressure. It's not at every pressure. Liquids, it's not like at every pressure. Over a range of pressure, this is what is valid. Most of our real applications will be in that range. Therefore, we neglect the pressure variations on density. But you need to consider the temperature variations. That's very important. You should not neglect temperature variation when you are working with liquids. But for gases, you have to be very, very careful. Whether you play with pressure or temperature, you have to take into account the value of corresponding density. You have to take into account the corresponding density value in the case of gases. Whereas in the liquids, no problem, no worry. Only for temperature change, you have to take into account the density value for a range of pressures. It's not like extreme pressures you are going to see. For a range of pressures, it's fine. The density won't change much for liquids. Density won't change much for liquids. So these kind of fluids are called as incompressible fluids. I'm just giving a term here. These kind of fluids are called as incompressible fluids. That means fluids whose density doesn't change with pressure are called as incompressible fluids. Whereas fluids which change, they're called as compressible. Any questions? Anywhere, any doubt? Any doubt?
No.
Okay, good. So that's why there is a last chapter I have given you, like chapter name is compressible flows, compressible flows. So where we'll be dealing mostly gases, air and all, where density has to be taken care. That's very important. It's a complicated problem. Up to first 5 chapters, we don't bother about density variation. We assume that the density, whatever you are written here, like 1,000, 1 and all, they are fixed. They are fixed in these 5 chapters. Whereas in the 6th chapter, where you are going to work with gases and air, particularly gases and air, where the pressure and temperature effects are very high, which leads to density changes. So therefore, that particular kind of subject is technically called as compressible flows. Compressible flows are gas dynamics. Gas dynamics. That's what, Deepak, what I told is over a range of pressures. It's not like at every pressure, you cannot assume it as an incompressible. Over a range of pressure, most of our real applications, not like extreme applications, most of our real applications, you will be seeing a liquid density doesn't change much when you change with pressure. But it changes as soon as you change the temperature. Like if you heat a water, you see a density change. Whereas if you change the pressure of a water a little bit, 1, 2, 3 bar and all, you don't see much change of density of water. It remains at 1,000. But if you see the if you change the temperature, you will definitely see the density of water will change. Understood? Clear, Deepak? Whereas for gases, it's not like that. Even though you change 1 bar also, bar and all it's a common unit for describing the pressure, for calculating the pressure. That's why I'm talking with bar, which we will see a little later. But if you change the pressure or a temperature, doesn't matter, you will see a change in gas density. You will see a change in gas density. So that kind of fluid mechanics, which is little complicated, that is very clear from the story itself, because you need to talk density separately. It's not like every time you cannot assume the density same, which is much comfortable in learning the things in the first 5 chapters. Whereas in 6th chapter, a little complex will come into picture. Apart from forces, you'll be having one more term called as density, which has to be talked at every point of time. Because it is changing. Each and every time it is changing, as well as each and every position also it will be changing. We'll see those kind of things a little later. That kind of physics or that kind of subject is called as compressible flows or gas dynamics. Compressible flows or gas dynamics. Fine, clear? Any doubt? So that's why I need to give, whenever you mention a density of a particular fluid, you should represent at what pressure and temperature you're talking at. So when I talk water and air of these kind of values, I need to mention here a pressure as 1 bar and temperature as a room temperature 25 degrees centigrade. And these are not valid at every pressure and temperature. Particularly for gases. Very, very important. Please be careful. And this story is very important. Compressible, incompressible. If it is changing with pressure, that is compressible. If it is effect is not changing with pressure, that is incompressible. Any questions anywhere? Any doubt? This is very important. And don't bother about the second half now. That is the gases, compressible and all. We'll see this thing little later, but the primary focus will be on this. But in these also, we'll deal with some gases where we are not going to work with high range of pressures, where the density changes large. Those kind of applications we are not going to see here in the first half. But we deal with gases also, where pressure changes are not much. Temperature changes are also not much, which leads to incompressible things. That means you are not going to talk about much about density variation. We assume the density is constant, but we'll play with the remaining properties. Are you guys catching the things what I'm talking about? In the first half, we don't focus on density variation. We assume the density is constant. It's not changing much because you are not going to see a problem where your pressure and temperatures are varying a lot. But in the second half, like the last chapter, where density and temperature, pressure and temperature changes are changing a lot, which leads to density changing a lot. So that kind of problem we'll see a little later. But in the first half, we'll completely focus on density constant problem. Density constant problems. That means most of the things are under incompressible. Most of the things are under incompressible. That's very important. Are you guys clear what I'm talking about? Anybody having any questions, any doubt here? Fine. If it is clear, let us see the next one. If you want, you can add one more fluid here, one more common fluid, which is mercury in this fluid mechanics. Density of mercury. We know the symbol for mercury, which is Hg, which is 13600. This is a standard number at these kind of pressure and temperature, kg per meter cube. I'm just giving you the number so that you can feel the numbers. You can feel the numbers. If I go for a gram per centimeter, it becomes 13.6. 13.6 gram per centimeter cube. 13.6 gram per centimeter. See the number. For water, it is 1000, whereas for mercury, it is 13,000, almost 30 times more. Please be careful with that. Next, coming to the next property, which is weight density. Instead of mass density, I'm talking about weight density. Weight density, generally used with a symbol called, a different symbol called gamma. Gamma. The name itself tells you it's mass density. That's why mass per unit volume. Now it's weight density, weight per unit volume. Defined as weight per unit volume. Weight per unit volume. So gamma equal to weight by volume. So instead of calculating mass, the kgs, now you calculate weight, that is Newton. Weight units is Newton, mass units is kg. So which leads to units of gamma as Newton per meter cube. Newton per meter cube. This is SI unit. You can convert into CGS, which is a Newton conversion to CGS. Anybody? How to convert Newton into CGS? Anybody? Dyne, right? 1 Newton is 10 power 5 dynes. 10 power 5 dynes. This kind of basic things you should know. 10 power 5 dynes divided by 1 meter cube. Again, it is 10 power 6 centimeter cube. It is equal to 10 power minus 1 dyne per centimeter cube. 10 power minus 1 dyne per centimeter cube. This is a conversion. Previous discussion is rho. So gamma equal to rho g. This is a kind of common expression we use, gamma equal to rho g. gamma equal to rho g. Clear? So again, from this we can write, since gamma is rho g, we know rho is a function of pressure comma temperature from our previous discussion. Pressure, temperature for rho, because rho is sitting here. On the top of that, you are having g here. On the top of that, you are having g here. So therefore, we are having one more thing, which is a location. Where you are calculating is also very important, because we know a g value for on Earth is different from Moon. It's almost 1/6. You might have learned in your school or physics. So that's why when you are calculating weight density gamma, it should be clear with pressure, temperature, as well as the location, which is very important. So there is an extra thing, but if you're working on a given Earth, it doesn't matter. The value of G is 9.81. It's a standard value, meter square per second. That is known for us. But if you're going for, suppose it's one planet or another planet, you need to be very careful when you're dealing with gamma or weight density. But it's again function of pressure, temperature, as well as location. Let me give you some value of gammas, knowing the densities of the previous fluids at these kind of pressure and temperature. If I go for gamma of water, which is equal to 1000, suppose on Earth, 9.81, which is equal to 9810 Newton per meter cube. Or if you want to go for a CGS, 981 dyne per centimeter cube. 981 dyne per centimeter cube. If I go for air, it's simply almost 1/1000 times, which is 9.81, because density is 9.81 Newton per meter cube. It's like 1/10. So therefore 0.981 dyne per centimeter cube. Similarly, you can write for mercury also. Mercury, which is equal to 13600 multiplied by 9.81, some dash Newton per meter cubes, which is equal to, divided by 10 will give us dyne per centimeter cubes. Can you please tell me how much Newton per meter cubes for mercury? Anybody? Can you please tell me what is the value of that?
133,416.
133
416.
33413 6. Okay, good. Thank you. 133,416 Newton per meter cubes for a mercury. It will be 13341.6. It's almost 1/10. So these kind of conversions you should know. Some problems while solving, you need gamma value. Some problems you just need rho. That depends on the type of problem. We'll see those kind of things a little later. So, but you should know the conversions. If I know density, how to calculate gamma, or if I know gamma, how to calculate density, both the conversions has to be known in hand. All these values again are the same standard pressure and temperature. Please be careful. These are not valid at every pressure and temperature. These are at 1 bar and 25 degrees centigrade. 1 bar and 25 degrees centigrade. And the next property we are interested here is very important, which is a specific volume. Specific volume. Specific volume. We use, whenever a specific comes to a given property, we use things with small letters. That's just kind of tradition we follow. So this is volume. So therefore small v. Small v. So specific means we know that, which is defined per unit mass. Per unit mass. So please be careful with this. Wherever you see specific, so specific enthalpy per unit mass, specific energy per unit mass, specific kinetic energy per unit mass. So whenever you say specific means, it means per kg of mass, how much is the property value. That's the meaning of that specific. There is nothing, a confusion in that. Okay. Always please go with blindly this kind of statement. So specific volume means defined as volume per unit mass, defined as volume per unit mass, volume per unit mass. So therefore small v is defined as capital V divided by M. Capital V divided by M. Or the same thing can be written as 1 by rho. Correct? Because we know mass by volume is a rho. It's just an inverse of that. So therefore 1 by rho. That means if I know density, or if it's just a conversion from one to the other. If I know specific volume, I'll get density directly by taking an inverse of that. In some situations, you need specific volume. Just take an inverse of a density, you will get the value. Again, units are like just an inverse of density. So therefore, it becomes meter cubes per kg. If you go for a CGS, a 10 power 6 centimeter cube divided by 1000 grams, which leads to 10 cube centimeter to gram. Instead of 10 power minus 3, you are having 10 cube now compared to your previous case. Similar kind of conversions can be done for water and air. Suppose say, if I take water, specific volume of water, which is equal to 10 power minus 3 now because of 1 by rho. Okay. And similarly, specific volume of air. Specific volume of air, it was 1. So again, it is 1. Again, it is 1. Any questions? Please be careful with the conversions. So don't confuse in the exam one to the other. Sometimes or some problems while solving, you need density value. Some problems you need specific volume value. Specific volume value. So you should know the conversions. And the next property we are interested here is, the relative density. Relative density. In some textbooks, they use with a different kind of terminology, which is the specific gravity. Relative density. The symbol mostly will be RD if I use relative density. Specific gravity means SG, but mostly you will see SG. Mostly you will see SG in the standard notations and all. Standard notation and all. Relative density or specific gravity, which is defined as weight density, that means the gamma of an unknown fluid. Basically, I should include one more term here, defined as the ratio of weight density of an unknown fluid to weight density of a standard fluid. This is a definition. Please be careful with the definition. A ratio of weight density of an unknown fluid to weight density of a standard fluid. So that means SG, weight density or specific gravity, is defined as gamma of some unknown fluid to gamma of a standard fluid. Standard fluid. So the standard fluid, people prefer it as water. Water. So if I take, suppose, say, in a expression form, gamma means rho g. So rho g of some unknown, some x, suppose say x I'm choosing like unknown. divided by rho g of water. Rho g of water. So if I assume that both the fluids are on the same planet, suppose the Earth, a g will be cancelled off, which leads to, instead of weight density, they are converted into mass density. So rho of x to rho of water. This rho of water, we know it as in a SI units, which is 1000. So rho of x can be calculated using, if I know specific gravity from the experiments, this x and that x will be confused. So this is Sg multiplied by 1000. Sg multiplied by 1000. So in some questions, they give you the specific gravity, but to calculate or to solve the problem, you need density value. So how to convert that specific gravity to density means multiply by 1000, you'll get the value of density of the required fluid. Density of the required fluid. If you want to know, for example, specific gravity of water, it's very straightforward now. That means X is same as water, which leads to 1. And if you want to say, go for mercury, specific gravity of mercury, suppose say, which is 13600 divided by 1000. So specific gravity of mercury comes out as 13.6. So please be careful. The numerator and denominator having gammas. There is no extra term. So therefore, this Sg doesn't have any units. That's very, very important. Don't use any units to describe Sg. Sg doesn't have any units. No units. No units. So if you go for air, suppose say Sg of air, which is 1 divided by 1000. 1 divided by 1000. Like that, you can describe Sg for any fluid. You can define Sg for any fluid. Any fluid. Any questions up to now? Anywhere, any doubt? Is it fine? Are you guys following the things? Is my pace okay? I mean, slow, fast, anything that you want to add?
Specific gravity of air, it should be divided by each. It should be divided by 1 by 1. How it become 10 power 3?
Water is 1000. We know for air it is 1.
Yeah, for the standard fluid is defined as, for liquid it is water, for gases it is air.
Yeah, that again comes in the kind of context. Like there is nothing like what you see if you take different kinds of data handbooks. In that data handbook, people define, like in this data handbook, the standard fluid you are using is water. In these kind of data handbook, the standard fluid you are using is water. But I'm just generalizing the context of liquids only, because we don't see much about gases in this first part of fluid mechanics. But as you said, if you go for different gases, suppose if you want to know specific gravity of nitrogen, then you write it as density of nitrogen to density of air only. That is correct. Exactly what you said is correct. But what I'm talking here is particularly only for water. If I'm having only water as a standard fluid, then if I choose different kinds of fluids as unknown fluids, how the specific gravity looks, that's it. What you said is exactly correct if I'm having different kinds of gases. But I'm not dealing with gases, particularly in this particular chapter or first part of fluid mechanics, because it is completely out, because all these properties will change pressure and temperature. But in the first part of the fluid mechanics, we generally don't want to change the density because it's a highly complex problem. That will be dealt in the next part. So therefore, we completely focus on the fluids whose density is constant for a range of pressures and temperatures. Understood? Clear? Hello?
Yes,
Who
sir.
raised the question? What you said is exactly correct, but I'm not talking about different gases now. I'm just focused on, if water is a standard fluid, how the specific gravity is. But if you're going with multiple gases, then you need to account, take a standard fluid as air. You need to compare with respect to air, how the density will be for different kinds of gases. But that is a different kind of story, which we are not into that. Any questions? Anywhere, any doubt? If you want, you can include here. For liquids, but mostly we'll be seeing liquids only. That's why. Liquids, a standard fluid will be water. If it is gases, a standard fluid will be air. Standard fluid will be air. That's why, again, if you go for a specific gravity of air, if you choose air as a standard fluid, a specific gravity comes out as again 1. Specific gravity again comes out as 1 in the context of gases. In the context of gases, it's just a reference. There is nothing big about air or water. It's just a reference. With comparing water, how much is that? With comparing air, how much is that? That's it, nothing more than that. Just a ratio. So, any question here? Anybody, any doubt? Is it okay? Everybody clear? Fine. If it is clear, let's jump into the next property. Let us jump to the next property. Very, very important property, which is viscosity. Viscosity. The next property we are interested here is viscosity, defined with mu. The pronunciation will be mu. It's similar to the friction coefficient, what you have seen in your solid mechanics or engineering mechanics, correct? In your solid mechanics or engineering mechanics, the friction coefficient was mu. A same context here, a viscosity property is defined with a symbol called mu, mu. Okay, let me define first this. What is this means? It's defined as a property of the fluid, defined as the property of the fluid due to which internal resistance is offered between the fluid layers. Between the fluid layers. That's very important. The statement is very important. Between the fluid layers, there is a resistance. Because of what means a property called viscosity. A property called viscosity. This is very similar to the friction, what you have learned in your solid mechanics. Like if you have two solid bodies which are in contact, and one body wants to move relative to the other, at the contact will be having a force, tangential to the surface, but opposite to the motion of the body. Let me repeat once again. In a solid mechanics problem or engineering mechanics problem, when two bodies are in contact, when two solid bodies are in contact, and if one body tries to move relative to the other, at the contact of the surfaces, at the contact of two surfaces, you have a force opposing the motion. That means the direction of the force will be opposite to the direction of the motion. That kind of force we framed in a kind of subject like solid mechanics or engineering mechanics as frictional force, Like the same way in a fluid mechanics, when one layer of the fluid wants to move relative to the other, there will be some friction offered by one layer of the molecules to the other layer. That means it doesn't allow that easily to move. There will be some resistance. A fluid has to spend some energy to overcome that resistance, has to spend some energy to overcome that resistance because of a property called viscosity. because of property called viscosity. If this property is not there with the fluid, then the fluid is easy to move. There is no problem. There is no problem. But because of having a property called viscosity, there is a resistance offered by a layer of the fluid on the other layer, due to which there is a slowing down action will come into picture. There is slowing down action coming to picture. That means, suppose say you have a plate something like this, a plate something like this. So there's a flow coming like this. Suppose from a left, it's going towards right. It's going towards right. So if I take, suppose at a particular x, suppose say, what I'll get a velocity profile will be something like this. I'll get a velocity profile something like this. Which means if I take some two fluid elements out, I'm having velocity something like this. One is suppose a u, the other one is u plus du. And these suppose are divided by, I mean differentiated by some distance called dy. So it is y direction. Y direction. So there is a relative velocity happening here. All the fluid layers are not moving the same velocity, even though initially they're having the same velocity at every y. As soon as it sees the plate, because of the property called viscosity, between the fluid layers, there is a resistance. There is a resistance offered by one layer of the fluid on the other, due to which there is a relative velocity concept coming to picture. Relative velocity coming to picture. Relative velocity concept coming to. This is very similar to your friction concept, what you have learned in your solid mechanics. Nothing new here. But the thing is, here this is generated because of the property of the fluid. Are you guys able to catch the point? Because of the property of fluid called viscosity, we're going to see this kind of story. If this property is not there, then the things will be something like this. This is when viscosity is 0. This is when viscosity non-zero. Fine. But in reality, any fluid you take, whatever the fluid you want to talk about, you will be having viscosity greater than 0. You will be having viscosity which is non-zero. So always you will see in reality a kind of problem, something like this. But this is what is idealized problem. Idealized problem. So that's why these kind of problems comes under inviscid. That means you are not talking about, or you are not including viscosity. That's why this is what is inviscid fluid dynamics. Whereas this is viscous fluid dynamics. Are you guys able to catch that point? That's why the chapter was divided into 2 parts. One is inviscid fluid dynamics, where you neglect the viscous effects and you assume everywhere the velocity is same with respect to y. Whereas in a kind of problem in reality will be the first one where I have given a tick mark, where you see velocity changes with y because of the property called viscosity. So that is creating more complex to the existing problem. That is creating more complex nature to the existing problem. So that's why those kind of problems will be dealt separately under a different part of the fluid mechanics, which is viscous fluid dynamics. Which is more complex, a lower one or upper one? What do you guys say? Where the problem will be more complex?
Upper one.
Upper one, obvious. Very good. So that's why means the main interesting part of the syllabus will be we are slowly increasing the complexity. We're starting with statics, where this kind of story won't be there at all. Then we jump into dynamics. First half will be inviscid, where you see a bottom part of the story. No viscosity. We assume that no viscosity, but in reality we have viscosity. But that's why this is called as idealized problem. Please be careful with that word, idealized problem. That means we are idealizing the reality. That means we are going to an extreme condition. If suppose a viscosity is not there, what will happen to the problem? That's what is the bottom one. That is what is inviscid fluid dynamics. Then we take into the viscosity, which is a real problem. You see a different kind of story. which is more complex than the existing one. That is what is viscous fluid dynamics. That is what is viscous fluid dynamics. So that is coming because of a property called as viscosity defined with mu. Defined with mu. So due to this viscosity, obviously you will see there is a shear stress. That's what I have discussed already when we talked about differences between fluids and solids. When one layer of the fluid moves relative to the other, you will be seeing a kind of stress called as shear stresses. Is it correct? So that's why here we're going to see different kinds of fluids now. I'm taking a fluid called as a Newtonian fluid. I'm taking a type of fluid called as Newtonian fluids, which means fluids which obey Newton's laws. Newtonian law. Obeys a Newtonian law are called as Newtonian fluids. A fluid which obeys a Newtonian law are called as Newtonian fluids. What is this Newtonian law means? The value of shear stress that is produced here, the shear stress produced here is directly proportional to shear strain, a rate of shear strain. Here you should not say shear strain in fluid mechanics. It is a rate of shear strain. If you see for a particular fluid from experiments, this kind of story, a shear stress proportional to rate of shear strain, those kind of fluids are called as a Newtonian fluids, and the kind of law is called as a Newtonian law. Are you guys clear? Understood? Everybody? Fluids which obey a Newtonian law, that is shear stress directly proportional to rate of shear strain, are called as Newtonian fluids. Why the shear stress is coming to picture means one layer is moving related to the other. Whenever one layer moves related to the other, you will be having shear stress or shear force. That's what our basic thing from your engineering mechanics or solid mechanics. Due to this shear stress or shear force, in fluid mechanics, obviously, you will be having a shear strain which varies with time. That's why this is called as a rate of shear strain. Is it clear? Now, one important question I want to ask here is, I have two fluids, say a fluid 1 and fluid 2. Let us assume that one is water, the other one is air, just for understanding purpose. I have applied same shear force. Say here also tau, here also tau. Do you expect the same rate of shear strain or different? Different. Is it correct? Everybody understood this statement? I've kept the tau same. The left hand side tau same for both the fluids, both water and air. But I'm seeing different rate of strain. The shear strain, what I'm seeing here, the rate of shear strain, we'll see this a little later. Rate of shear strain is defined by d phi by dt or d theta by dt, whatever may be. In water is not equal to d phi by dt in air. Because something is coming into the picture which talks about the property of the fluid. Some property has to be accommodated in the previous expression, so that even though the shear stress value in the left hand side is same, the rate of shear strain in the right hand side is different. To make sure the left equal to right, some property value has to be taken into account, then the tau value will become same. Are you guys able to agree with my statement? I'm keeping the left hand side same for both the experiments. When I'm doing an experiment with fluid 1 called water, I'll repeat the same experiment with a different fluid with air by keeping the same tau value. So tau value is in my hand. That is by applying some shear force that is in my hand. But what the result coming out of is not in my hand. That is completely governed by the type of fluid what you are using. I'm seeing a rate of shear strain different between water and air, even though I kept the same force by area value same. That means shear stress value same, which means something has to be included in that equation what you have written already as a directly proportional, which takes into account this kind of nature of the property of the fluid. That is what is called as viscosity. So therefore, what we'll do now, we'll modify the existing equation. We'll modify this existing equation as tau equal to mu times of a rate of shear strain. Are you guys clear why I'm writing mu now? Actually speaking, there is no importance of mu when you write like this. But when you do an experiment, something like this, fluid 1 and fluid 2, which are not same, there is an importance of mu coming to picture. There is an importance of mu coming to picture. That is very important. When you're working with the same fluid, it's fine. Mu doesn't matter there. But when you keep the same tau value, but playing with different fluids, there is something related to mu between these two fluids. It's very, very easy from our common sense. We can say water is, you need to apply more force for the water to move, whereas air, it is easy to move because the viscosity of water is higher compared to viscosity of air. Viscosity of water is greater than viscosity of air. See, if I keep the same tau value between these two, if this is the conclusion which we know already, what do you expect the rate of shear strain? Are you getting my question? If I keep the same tau between both the fluids, fluid 1 and fluid 2, same tau. I've given you already the rate of shear strains are different. But after seeing this kind of expression from our common sense, viscosity of water is greater than viscosity of air. What do you expect between these two? Which is higher or which is lower? Are you guys getting my question?
Shear force on water would be higher.
No, I'm keeping shear force same. But this is what is known from our real experiments. Viscosity of water is greater than viscosity of air. But what do you expect the deformation? Where you see more deformation, where you see less deformation?
For air, more deformation.
For air, more deformation. To accommodate the same tau value, since the air viscosity is less, it deforms more. So you expect a rate of deformation or rate of shear strain for air will be greater than the rate of shear strain for water. Under what condition? That is very important. Under what condition?
Same
tau. Same tau. Because this is what is governing this, or this is what is driving this to happen, something like this. The viscosity is a key parameter in order to see the deformation, in order to see the shear deformation. If suppose the viscosities are same, then the result will be different. Suppose if I take honey, what do you expect? Honey, the same experiment if I include honey. Come on, man. You know, everybody knows, I think, honey. In our home, we use honey, ghee and all. What do you expect? Whose viscosity will be more?
Honey will be very less.
Less or high?
Viscosity is very high. So
yeah, viscosity will be high. That means to deform honey, I need to apply more force. Is it correct?
Yes.
Or for the same force, it deforms less.
Yes.
Both are same, right? To deform more, I need to apply more force. Or for the same force, it deforms less. Everybody catching the point? This is very, very important point. This is where student has to be very careful. This is where this is what you will see in reality. It need not be honey, water, air and all. You'll be seeing something else. Some petrol, diesel, kerosene and all. If you go to automobile industry. So you need to be very careful with these kind of properties. Whether it is highly viscous, less viscous, higher density, low density, all these kind of things has to be taken care. Viscosity is very, very important. If viscosity, if you are neglecting, the story will be something like this. The bottom part in the yellow color, idealized one. But that is not the reality. A reality will be something like this, which is connected to this kind of problems a little later. But this expression is very, very important to understand our entire analysis. From now onwards, we are going to use this expression called tau equal to mu times of rate of shear strain very rigorously. Assuming that the fluids, whatever you're going to talk about, they're Newtonian fluids. That means they're obeying a law called Newtonian law. Please be careful. You are going to work with the fluids which are satisfying these laws. which is Newtonian law. There are some fluids which doesn't satisfy. They are called as non-Newtonian fluids. Non-Newtonian fluid. That means tau is not proportional to rate of shear strain. That's a complex problem which you are not going to deal in an undergrad class. That means B or B.Tech level class. Those kind of problems will be dealt when you go for higher education. That's a different research area, which is non-Newtonian fluids. We are not going to bother about non-Newtonian fluids here. The entire study of our fluid mechanics in this kind of course, especially for GATE or IAS exam, will be completely governed by an assumption called a Newtonian fluid assumption. So please be careful with assumptions. Already I have introduced total 2 things. This is the third one. 2 things means first one is incompressible, compressible. The second one is viscous, inviscid. Now it is Newtonian. These kind of words are very important when you are reading a question in a question paper. Please be careful. First one was incompressible, compressible, viscous, inviscid. Now it is Newtonian, non-Newtonian. Newtonian, non-Newtonian. So our entire fluid mechanics will be something like this, like Newtonian plus incompressible plus inviscid. Okay, it can be Newtonian plus incompressible plus viscous. Clear? Or Newtonian plus viscous plus incompressible. Okay, or Newtonian plus you have the last chapter. Is it correct? Do you guys remember the last chapter? I think it's same, right? Sorry. 1 second. Skip these 2. A Newtonian plus incompressible is over, right? Now I need to use compressible. 1 second. Yeah. I'll include now compressible plus inviscid, Newtonian plus compressible plus viscous. Are you guys able to catch the things? Newtonian is common. We are not going to deal with the non-Newtonian fluids at any cost. That's fixed. Plus incompressible plus inviscid. That's a very simple problem. You are not going to bother about density. You are not going to bother about viscosity. Are you guys clear? If you are not bothering about viscosity, there is no discussion about Newtonian. We can leave about that. But I am just adding there. Next problem. You want to think about viscosity. So therefore viscous, Newtonian, viscous, but you are not going to talk about a fluid where tau is not proportional to rate of shear strain. So for Newtonian plus incompressible, density effects you are going to neglect. Next one, inviscid, no need of Newtonian and all, just leave about that. But compressible, you want to see density effects. The last very complex problem, density changes, it's highly viscous. Are you guys clear? Everybody? Any questions here? Anywhere, any doubt? Hello.
No.
Clear, right? These kind of statements are very important. In the exam, they'll use these kind of statements, whether they are incompressible, compressible, viscous, inviscid. Generally, less time they talk about Newtonian and non, because it's a common assumption in our entire fluid mechanics, which is a Newtonian. So therefore, nobody bothers about Newtonian and non-Newtonian. Okay. Most of the times we take this relation is valid. This relation is valid. Tau equal to mu times of rate of shear strain is valid. So therefore, no problem about that. A very good example for Newtonian fluids are water and air. That's why most of the times we use the applications for water and air. Are you guys clear? The Newtonian fluids, very good example are water and air. Water and air. These are very good examples for Newtonian fluids. There are many, but these are very good examples. That's why most of the problems what you see in upcoming classes dealing with water and air only. dealing with water and air only. We don't talk much about the blood. We don't want to talk about much about honey, all these kind of things. Understood the physical importance of viscosity now? Any confusion still? Means I want you guys to understand the physical importance, not the equations, not the statement. You should know what is happening in the backside. Using viscosity, what you really understand, that's very important. It's not like simply it's a definition or equation. What viscosity does in real problems is very, very important. What viscosity really does in real problems is very, very important. Fine. So now let us see what is the unit of viscosity. From this equation, let us see what is the unit of viscosity. Or before going for that, let us see what is the expression for rate of shear strain. Let us see what is the expression for rate of shear strain. Then we can come to the viscosity units. The rate of shear strain. Rate of shear strain. So let me take those two layers out, separated by a distance of dy with a relative velocity of du, So that means I have two layers. Which is u plus du. This is u. This is, I'm just zooming in the things. Whatever I have drawn already, I'm just zooming in. I'm drawing like this. Or you can convert this into something like this also, doesn't matter. In a relative elastic concept, this is du, this is dy. And this is what is your shear strain, which is say phi. And this kind of thing has happened when you waited a time called dt. I told you this fluid mechanics is completely governed by time. The strains, a shear strain, whatever may be, they vary with time. So this kind of thing has happened, or the du has generated compared to u over a period of time dt. That means this fluid layer has traveled a distance of du times dt. This velocity, I'm writing now this magnitude, I mean this length. This length value is du times dt. Everybody agrees with that? If I know this velocity over a time of dt, this might have traveled u times of dt. U times of dt. Whereas similarly, this is u plus dt times of dt. Du times of dt. That is known from our school level physics. If I know velocity time, I can calculate what's the distance traveled. What's the distance traveled by that corresponding body or fluid element or whatever may be. In this, a fluid layer. A fluid layer has traveled a distance of du times dt, the top one, because that is having an extra velocity of du. A bottom one, I don't want to bother because I'm taking a relative velocity concept. So therefore, no problem for that. So now I want this value. That's the question mark here. What is the value of phi over a period of time dt? That's the meaning of shear strain that you have seen in your engineering mechanics or solid mechanics. So the shear strain comes from your tan phi equal to the top is du dt divided by dy. Divided by dy. People use like this is very small deformation because element time is dt very small. People use like d phi just to go with the differential form. I'm writing like this. This is also because for a period of a very small time, you see a deformation very small. That's it, nothing more than that. This is again d phi. We know for very small d phi's, tan d phi equal to d phi because tan 0 is 0. Like the same way, very small angles, tan d phi is equal to d phi, which is equal to du dt divided by dy. So rate of shear strain, this is shear strain. A rate means you need to get into time. So d phi by dt equal to du by dy. This is very, very important. Are you guys able to clear? D phi by dt equal to du by dy. I'm just bringing this dt to left hand side because I want this kind of term called rate of shear strain. So therefore, using that Newtonian law expression, tau equal to mu times of, I can write d phi by dt or mu du by dy. Both are same. Both are same. You can use any of this, but you should know both expressions. Please be careful. Sometimes they may give you what is shear strain versus time plot, and they may ask you what is the value of shear stress, or they may give you velocity versus y plot, and they may ask you what is the value of shear stress. Are you guys clear what I'm talking about? Understood? Any questions? Come on, man. Everybody clear? Ashwin, Balaji, Dinesh, any questions anywhere, any doubt? Is it okay? Somebody messaged. You can unmute and you can talk, no problem if you are fine with internet. Okay, clear, good. Okay, then we'll stop here. I think it's lunch break. We'll go for lunch and we'll meet at 3 o'clock. We'll continue the discussion from here because I need some more time. Okay, is it okay, everybody? We'll stop here. We'll meet at 3 o'clock. Understood? Yeah. See you at 3 o'clock. Bye.